Hello everyone, the Science Chef is here again. In this video, we'll be learning about the third part of a series on acids, bases and salts titled Neutralization Reaction and its Applications. Please go nowhere and we'll be right back after this timeout. If you'd like us to make more of these tutorials, like this video, subscribe to our channel and turn on your notification bell. If you would also like to watch our past tutorials on acids and bases, check the link in the description. In our last tutorial, we learned that a base is a substance that neutralizes an acid. Therefore, a neutralization reaction is defined as a reaction between an acid and a base to form salt and water. It is also the reaction that occurs when hydrogen ions from an acid combine with hydroxide ions from a base to form water molecules, as shown on the screen. There are many examples of neutralization reactions, and we have discussed some of them in the first two parts of this series under the properties of acids and bases. Other examples are reaction of hydrochloric acid and potassium hydroxide to form potassium chloride and water, reaction of sulfuric acid and magnesium oxide to form magnesium sulfate and water, the reaction between nitric acid and calcium hydroxide to form calcium nitrate and water, and the reaction of ethanoic acid and sodium hydroxide to produce sodium ethanoate and water. We can represent these reactions as ionic equations. An ionic equation shows what goes on in a reaction by showing just the ions that partake in the reaction. To write ionic equations, first break all the ionic compounds and those in aqueous state into their respective ions. Then strike out any ions that appear unchanged on both sides of the equation. These struck out ions are present in the solution but do not partake in the reaction. Hence they are called spectator ions. At the end, the ions left in the neutralization reaction equation will be hydrogen ions and hydroxide ions if the base is an alkali, or hydrogen ions and oxide ions if the base is an insoluble base. These ions combine to form water. In the first reaction between hydrochloric acid and potassium hydroxide, hydrochloric acid, though not an ionic compound but as a strong acid, ionizes completely in aqueous solution into hydrogen and chloride ions. Potassium hydroxide, a strong alkali, dissociates completely into potassium and hydroxide ions, while the salt potassium chloride becomes potassium and chloride ions in solution, and water, being a covalent compound and the liquid state, is left the way it is. Potassium and chloride ions, which appear unchanged on both sides of the equation, are struck out, leaving the hydrogen and hydroxide ions, which form the water molecules. Similarly, in the second reaction between sulfuric acid and magnesium oxide, the sulfuric acid breaks into 2 moles of hydrogen ions and 1 mole of sulfate ions. The magnesium oxide, an ionic compound, is made up of magnesium and oxide ions, while the salt, magnesium sulfate, is broken into magnesium and sulfate ions in solution. Magnesium and sulfate ions are unchanged on both sides of the equation and hence are struck out, leaving 2 moles of hydrogen ions and 1 mole of oxide ions, which combine to form 1 mole of water molecules. In the third reaction between nitric acid and calcium hydroxide, based on the balanced chemical equation, the nitric acid breaks into 2 moles of hydrogen ions and 2 moles of nitrate ions. The calcium hydroxide ionizes into 1 mole of calcium ions and 2 moles of hydroxide ions, while the calcium nitrate salt is broken into 1 mole of calcium ions and 2 moles of nitrate ions in solution. The calcium and nitrate ions appear unchanged on both sides of the equation, and so they are struck out, which leaves us with 2 moles each of hydrogen and hydroxide ions, which combine to form 2 moles of water molecules. Lastly, in the reaction between ethanoic acid and sodium hydroxide, the ethanoic acid, a weak acid, dissociates partially to hydrogen ions and ethanoate ions. The sodium hydroxide, a strong alkali, ionizes completely into sodium and hydroxide ions, and the salt sodium ethanoate exists as sodium and ethanoate ions in solution. The sodium and ethanoate ions are unchanged on both sides of the equation and are struck out, leaving 1 mole of hydrogen ions and 1 mole of hydroxide ions, which combine to form 1 mole of water molecule. Note that the neutralization reaction is not a combination reaction, as water is not the only product formed. As seen, a salt is always produced in addition to water. Neither is it a redox reaction because there is no transfer of electrons nor change in oxidation states of the elements involved in the reaction. To learn more about oxidation numbers and redox reactions, check the link in the description. Let's take a look at the energy change that occurs during neutralization, otherwise known as the heat or enthalpy of neutralization. The standard heat or enthalpy of neutralization, delta H n theta, is the amount of heat evolved when 1 mole of hydrogen ions from an acid combines with 1 mole of hydroxide ions from a base or alkali to form 1 mole of water at 25 degrees Celsius, 1 atm, and 1 molar solutions of the acid and alkali. Neutralization is an exothermic reaction, which means that during the process, energy is released to the surrounding in form of heat, and this is always confirmed by the warmness or hotness of the reaction vessel. The heat of neutralization of the reaction between a strong acid and a strong base is a constant with a value of about minus 57.4 kilojoules per mole of water formed. This is because of the complete ionization of the acid and base in solution. The value of the heat of neutralization for the reaction between a strong acid and a weak base, or a weak acid and a strong base, is not a constant and is less than that between a strong acid and a strong base. This is as a result of the partial dissociation of the weak acid or base in solution, which means there are lesser amounts of the ions in solution that will form water molecules than in strong acid, strong base reactions. The value of the heat of neutralization of the reaction between a weak acid and a weak base is the lowest, and is not also a constant due to the far fewer number of ions in solution. How to calculate the heat of neutralization will be treated under another topic, energetics, as it is outside the scope of this video. Let's look at some applications of neutralization reactions in our daily lives and environment. A common application of neutralization reaction is a treatment of indigestion using milk of magnesia. The milk of magnesia contains magnesium hydroxide, a base, while the indigestion is due to the secretion of excess gastric juice, which is hydrochloric acid in the stomach. So the magnesium hydroxide neutralizes the excess hydrochloric acid, thereby returning the stomach to its normal state. Another common application is the use of limestone to remove acidic impurities of silicon 4 oxide or sand from iron ore during the extraction of iron and making of steel. The limestone undergoes thermal decomposition in the blast furnace to produce calcium oxide, a basic oxide, which then reacts with silicon 4 oxide or sand and acidic oxide to form calcium silicate, a salt. The calcium silicate is removed from the blast furnace as slag. To learn more about the extraction of iron, check the link in the description. Also, the principle of neutralization reactions is applied in the removal of acidic gases like sulfur dioxide from flue gases at power stations using slaked lime or limestone before releasing the harmless gas into the atmosphere. This is known as the flue gas desulfurization. A flue gas is simply a waste gas given off through the chimney during any industrial chemical process. The manufacture of fertilizer from nitric acid and ammonia gas is also an application of neutralization reaction. The acid reacts with the alkaline gas to form ammonium nitrate, an important fertilizer. Similarly, phosphoric acid is made to react with potassium hydroxide to form potassium phosphate, another good fertilizer rich in potassium and phosphorus. Another important use of neutralization reaction is in the treatment of soil acidity. Usually, a soil can become acidic due to the excessive use of fertilizers or the effect of acid rain, and this can affect plants' growth. To neutralize this effect, slaked lime, that is calcium hydroxide, or quicklime, that is calcium oxide, or limestone, that is calcium carbonate, is added to the soil to reduce its acidity and make it suitable for planting. This is known as liming of soil. Finally, neutralization reaction is also applied in the test for carbon dioxide. Carbon dioxide gas turns lime water milky when bubbled into it. Carbon dioxide, an acidic oxide, reacts with calcium hydroxide, an alkali, which is the lime water, to form a milky precipitate of calcium carbonate. A precipitate is a solid substance formed when two solutions or a gas and a solution are mixed together. Do you realize that all the neutralization reactions discussed in this tutorial have one thing in common, which is the formation of a salt? It is therefore important to note that a salt is a constant product of all neutralization reactions, and there are some neutralization reactions that will not produce water due to the composition of the acid or base. If the acid does not contain a hydrogen ion, nor the base a hydroxide or oxide ion, then water will not be formed. Our next tutorial will be on pH and pOH and their calculations. Subscribe to our channel and turn on your notification bell to get notified when we publish the video. Until then, stay on top.